So far, we've taken a look at how we can compute partial derivatives for different surfaces, different functions of x and y. Now, we're going to continue to expand on this idea and cover some things that are similar to things we talk about in a Calc 1 class. One of the things you might remember back in a Calc 1 class was the concept of implicit differentiation. This concept loosely came about when you were dealing with equations which represented curves that were not functions. This is typically when we would use this approach. For example, back in a Calc 1 class, if I wanted to know slopes of tangent lines on a circle, I would first recognize that a circle is not a function. And so I could go ahead and maybe take that formula that creates the curve of the circle, and I could differentiate it implicitly. That is, by assuming that x was my variable and that y was going to kind of be treated like it was a function of the variable x. Well, notice that in 3 space, it's entirely possible to also have curves or surfaces that do not necessarily represent functions. For example, in the above picture, you can see that for every possible x, y point that I choose down in the xy plane, it looks like there's only one possible z coordinate that can come out. But what if I had a curve that, or a surface that did something kind of like this, like a surface that like folded in half on itself, right? So I'm going to kind of imagine a surface like this. You could imagine that at some points, when I pick a particular xy, that might correspond to a z above it and a z below it. Or even simpler than this curve, or this surface, think about the surface of a sphere. That's kind of like the 3D version of the circle. And again, when I plug in one particular xy point, there's going to be multiple different z's that can be on that surface. And so that surface there is not representing a function. So can I still find slopes of tangent lines on that particular surface at various points? Well, sure. What I would have to do is take my derivative implicitly. So what I'm going to do here is here I'm going to be trying to find a partial derivative of z with respect to x. So I'm doing a partial derivative with respect to x. So I'm going to treat x here like it is my variable. And I'm still going to treat y like it's a constant. But what I'm going to do is I'm going to have to compute the partial derivative with respect to x of both sides of my equation. Again, x is going to be my variable. Y is going to be a number. And I'm going to pretend right now that z is some function that could be written in terms of a bunch of x's. So whenever I see z, I'm instead going to think stuff with x. All right, so let's see how this plays out. So if I did the derivative with respect, or the partial derivative with respect to x to the third, I would just get 3x squared. If I do the partial derivative of y to the third, if y is a number, that should get me 0. If I imagine z as a bunch of stuff with x to the third, I'm going to need to enact the chain rule. I would do 3 times stuff with x squared, and then times the partial derivative of that stuff with respect to x. So again, what I'm kind of imagining here is that I have something like, I have a formula. Let me write this here. I have like stuff with x and y raised to the third power. So like I have some formula in there, I'm not sure what it is. So when I take its derivative, I have to use the chain rule. Bring the 3 down to the front, leave the stuff with y, x and y, and then take the derivative of that stuff with respect to x. So that's kind of what's happening there with the z. The tough part here at the end is that here I'm going to have 6 times x times a number times stuff with more x's and y's. So I actually am going to have to make use of a product rule here. I'm going to go ahead and think about 6xy as one of the items in the product and z as the other. So I would have 6xy times the partial derivative with respect to z, or partial derivative of z with respect to x. And then I would have, let's see, the derivative of the red stuff would be 6y, because again, y is a number, x is the variable. and then just times z. So you can see here, this is my product rule that's in play there. Now, when I do the partial derivative on the other side, that's going to be super easy. I'm just going to get 0. So if the question now asks me to solve for partial of z with respect to x, I'm just going to have to move some things around. I'm going to go ahead and start by moving everything that doesn't have a partial derivative with z to the other side of my equal sign. You'll notice that means I have to subtract over the 3x squared, and I have to subtract over the 6yz. Everything that does have a partial with respect to x is going to be left over on this side, and I'm actually going to be able to factor out that partial. That would leave me with a 3z squared and the 6xy that I have over there. So now, to isolate that partial of z with respect to x, I can simply just divide by the set of brackets that I have. So I would get negative 3x squared minus a 6yz divided by a 3z squared plus a 6xy. Now, of course, you could maybe do some stuff here to reduce this fraction, factor out a 3 from top and bottom, but I don't really care. This is perfectly acceptable here as a partial derivative. It's kind of cool because we're, again, just using the idea of implicit differentiation that we would have seen back in a Calc 1 class.